Hi students, and welcome to this lecture which is known as Differential Equations. Now this lecture does not only form an integral part of calculus or mathematics, but we will also see that differential equations are widely applied to model natural phenomena, engineering systems, and many other situations. For example, in chemistry it is applied to the study of radioactive decay. In physics it's applied to Newton's laws of cooling. In mathematics you will see that they are applied in the study of orthogonal trajectories of curves. They are applied in population dynamics, quantum theory, heat transfer, in astrophysics, geophysics, and so many diverse fields. So that makes it very much important for us to study this chapter in depth. So let's begin. So once again, the very standard doubt: what are differential equations? We can say that it is an equation involving independent variable, dependent variable, and the derivative of dependent variable with respect to independent variable. So it is an equation and it involves the independent variable, the dependent variable, and the derivative of dependent variable with respect to the independent variable. In simple words, we can say that it is an equation that relates x, y, and different orders of derivative of y with respect to x. So this is an equation in which you will find x, you will find y, and you will find derivatives of y with respect to x. This could be dy by dx or d square y by dx square or d cube y by dx cube and so on. For example, if I say x times dy by dx plus 2 times y equal to 0. Here we see that this is an equation in which we find x, we find y, and we also find the derivative of y with respect to x. Similarly, if we consider this equation d square y by dx square equal to x plus y, again you have x, you have y, and you have the second derivative of y with respect to x. So these all are examples of differential equations. The next is order of differential equation. Now order of differential equation is the highest order derivative of the dependent variable with respect to the independent variable. So we can say that the order of the highest order derivative of dependent variable is y with respect to x. So if I say that d square y by dx square plus y equal to 0, now this is second order, because the highest order derivative here is this one and this is a second order, and so we can say that this entire equation has an order of 2. Similarly, if we consider this equation d cube y by dx cube minus d square y by dx square plus y equal to x, here we see that this is a third order, because the highest order derivative here is d cube y by dx cube. We also have a second order derivative, but since we have a third order derivative, we take this into account because this is the highest order derivative, and so the order of this entire differential equation becomes 3. The next concept is degree of a differential equation. Now, the highest power of the highest order differential coefficient appearing in the polynomial form of the differential equation is called as the degree of differential equation. So it is actually the highest power of the highest order differential coefficient. So what we can say is the degree of differential equation is nothing but the highest power of the highest order differential coefficient. So for example, if we consider this equation y plus dy by dx whole square plus x square equal to dy by dx. Now we see that this is a first order differential equation because the highest order differential is 1 dy by dx, and actually we see that this is having a power of 2, so the degree would be 2. Thus we can say that the degree of differential equation is the highest power of the highest order differential. There is a term dy by dx here also, but we consider the highest power of highest order differential to be the degree of differential equation. Thus here 2 is the degree of differential equation. Now forming differential equations. Now how are we going to form differential equations? Here what we do is we differentiate the equation of curve till the unknown constants are eliminated. To form a differential equation, first of all we must have an equation of curve and it must be having some unknowns. So what we do is we differentiate this equation as many times so as to remove those unknown constants. For example, if we consider this equation y equal to ax. Now this equation y equal to ax represents a family of straight lines. Here we see that a is an unknown constant. So what we do is we differentiate both sides with respect to x. So dy by dx would be equal to a. Now we know the value of a, which is dy by dx. We substitute this value over here to get y equal to x times dy by dx, and hence this is a differential equation. So the differential equation of family of straight lines given by the equation y equal to ax is y equal to x times dy by dx. Let's consider one more example. Find the differential equation whose solution represents the family of curves y equal to a times sine of x plus b. Now we have y equal to a times sine of x plus b, and we have to find the differential equation whose solution represents this family of curves. So we write y equal to a times sine of x plus b. Let us say that this is number 1. Here we see that a and b are two unknown constants, so we need to eliminate these two unknowns. What we do is we differentiate both sides with respect to x. Thus dy by dx would be equal to a times cos of x plus b, as a differential coefficient of sine of x plus b is cos of x plus b. So dy by dx equal to a times cos of x plus b. Again we differentiate with respect to x. So d square y by dx square would be equal to minus a into sine of x plus b. Let us name this as equation number 2. Now we see that a times sine of x plus b is equal to y, and minus of a times sine of x plus b equal to d square y by dx square. So from 1 and 2 we can write as d square y by dx square is equal to minus y, or d square y by dx square plus y equal to 0. This is the differential equation whose solution represents the family of curves y equal to a times sine of x plus b. Thus this is a second order differential equation where the degree is 1. Now we are going to see how to solve differential equations. The entire chapter is actually based on solving differential equations. So one by one we are going to see different methods of solving differential equations. The first method is separable variables. So if the differential equation is of the form of dy by dx equal to f of x comma y. So if we have got the differential equation of this form, which can be reduced to the form of dy by dx equal to g of x into h of y, then we write dy by h of y equal to g of x into d of x, and this way we have a function of y with dy and we have a function of x with dx, and this can be easily solved. So in the method separable variables, what we have is we have dy by dx equal to some function of x into some function of y. So this can be separated, and the function with y can be brought to the side of dy and the function with x can be brought to the side of dx. So we have separated this function into two parts, one part comprising of y with dy and the other part comprising of x with dx. Let's try to solve an example that will throw more light on this. This problem appeared in IIT JEE 2007, and it says that the differential equation dy by dx equal to under root of 1 minus y square divided by y determines a family of circles with option number A is variable radii with a fixed center at 0, 1, variable radii and a fixed center at 0, minus 1. Option number C is fixed radius 1 and variable centers along the x-axis, and option number D is fixed radius 1 with variable centers along the y-axis. So in this problem we have been given a differential equation and we have to find out which of the four options is correct. So the first step is to solve this differential equation. Now dy by dx is equal to under root of 1 minus y square by y. Now we can say that dy by dx is equal to a function of y into a function of x. Here a function of x is nothing but constant. So what we do is we bring this expression which comprises only of y to this side of dy and we bring dx to this side. Thus y times dy divided by under root of 1 minus y square is equal to dx. Now we integrate both sides. So the integral of this is minus of under root of 1 minus y square. The integral of dx is x plus a constant of integration. So minus of under root of 1 minus y square is equal to x plus c. Now we square both sides to get 1 minus y square equal to x plus c whole square, or x plus c whole square plus y square equal to 1. Now this is an equation of a circle, the center of which is minus c, 0 and the radius is equal to 1. Thus the differential equation when solved gives x plus c whole square plus y square equal to 1, which is the equation of a circle, the center minus c, 0 and radius 1. Now this is nothing but option number C, and so we can say that option number C is correct. Let's try to solve one more example. Solve the differential equation 1 plus 4x square into dy equal to y cube into x dx. So we have to solve this differential equation. The differential equation given is under root of 1 plus 4x square into dy equal to y cube into x into dx. We bring y cube to this side of dy and we bring this term comprising of x to this side of dx. Thus dy by y cube is equal to x times dx divided by under root of 1 plus 4x square. Now the integral of this part is very easy. For this part, let's do a substitution that let u equal to 1 plus 4x square. So we write 1 plus 4x square equal to u. So du would be equal to, we differentiate this to get 8x into dx. Now we substitute the value of x over here to get dy by y cube equal to 1 by 8 into du divided by under root of u. So what we do is we integrate both sides to get minus 1 by 2y square equal to 1 by 8 into 2 into under root of u plus k. K is again a constant. We again substitute back the value of u. So minus 1 by 2y square equal to 1 by 4 into under root of 1 plus 4x square. Thus this is the final solution of the differential equation under root of 1 plus 4x square into dy equal to y cube into x dx. So this was all about separable variables. The equations reducible to separable variables. Now in this method, we won't be given directly a differential equation which could be solved by separable variables. Here we have to perform some trick or some modification so that the equation reduces to a form that can be easily solved by the method of separable variables. But how we do that? Let's see. If the differential equation is of the form dy by dx equal to f of ax plus by plus c, that is dy by dx is a function of ax plus by plus c, then we cannot solve this by separating variables directly, as we cannot split it into a function of x and a function of y. But by substituting ax plus by plus c equal to t, we can reduce this into separable variable form. How? The differential of this would be a plus b times dy by dx equal to dt by dx. So we substitute the value of dy by dx in this expression in the form of dt by dx, and thus the differential equation would be in the form of variables x and t, and which can be easily solved by the method of separable variables. Let's try to see an example. Solve the differential equation dy by dx equal to cos of x plus y. So we have to solve the differential equation dy by dx equal to cos of x plus y. Can we solve this equation dy by dx equal to cos of x plus y by variable separable method? Yes, we can do that, but there is some modification involved. Let us substitute x plus y equal to t. So this is a function of x and y, and thus we substitute x plus y equal to t. Now differentiating both sides, we get 1 plus dy by dx equal to dt by dx. So this equation reduces to dt by dx minus 1 is equal to cos of t. Now we can say that this can be easily solved by variable separable method. So we bring 1 plus cos t to this side of dt and we bring dx to this side to get dt by 1 plus cos t equal to dx. Now this can be easily solved. What we do is we write cos t equal to 1 minus tan square t by 2 divided by 1 plus tan square t by 2, and then if we substitute tan of t equal to u, then we can easily solve to get tan inverse t by 2 equal to x plus c. Again t is equal to x plus y. So the final solution of this differential equation is tan inverse of x plus y divided by 2 equal to x plus c. Thus we have seen that through a slight modification, through the substitution, that is x plus y equal to t, we have reduced this differential equation to a form that can be easily solved through the method separable variable, and thus we get this final answer. The next type of method is for homogeneous differential equations of the first order. So any equation of the form dy by dx equal to f1 of x comma y divided by f2 of x comma y, where f1 and f2 are the homogeneous functions. Now what is a homogeneous function? Homogeneous function is a function such that the addition of the exponents of x and y is constant throughout. So differential equations of the form of homogeneous functions of first order can be solved by using this method. Now we write dy by dx as equal to f of x by y by dividing both the functions by x to the power of n. So if this equation is of the degree n, then what we do is we divide the numerator and denominator by x to the power of n, and thus we express dy by dx as a function of x by y. In the next step, what we do is we substitute y by x equal to t, and so this is the way we solve such kind of homogeneous differential equations of the first order. So let's try to see an example. Solve the differential equation dy by dx equal to x square plus y square divided by 2x square. So dy by dx is equal to x square plus y square divided by 2x square. Now we see that the numerator and the denominator both are some functions and which are homogeneous in nature. This is because the exponent of x is 2, the exponent of y is 2, and the exponent of denominator is also 2. So this is a homogeneous equation. Now what we do is we write y equal to t times x. So dy by dx would be equal to t plus x times dt by dx. So dy by dx is equal to t plus x times dt by dx. We substitute this value over here to get t plus x times dt by dx equal to 1 plus t square by 2. This is because we substitute y equal to t times x. X and x gets cancelled from the numerator and denominator, and what we get is 1 plus t square by 2. So taking t to this side, we get 2 times x into dt by dx equal to 1 plus t square minus 2t. We bring this term to this side and we bring x and dx to this side of the equation to get 2 times dt by 1 plus t square minus 2t equal to dx by x. Now this could be written as t minus 1 whole square, and so when we integrate both sides, we get minus 2 by 1 minus t equal to ln x plus c, because the integration of 1 by x is ln x. Again we write the value of t as y by x, so minus 2 by 1 minus y by x is equal to ln x plus c, or 2x equal to x minus y into ln x plus c. Thus the solution of dy by dx equal to x square plus y square divided by 2x square is 2x equal to x minus y into ln x plus c. The next method is equations reducible to homogeneous equations. Now we won't be getting equations that are directly homogeneous, but we reduce those equations to a form that could be easily solved, and that form is the homogeneous equations. So the differential equation of the form dy by dx equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2. So if we have a differential equation of this form, then we use this method to solve it. Now your condition is if a1 by a2 is not equal to b1 by b2. So the ratio of coefficients of x is not equal to the ratio of coefficients of y. In the next step, what we do is we write x equal to capital X plus h and y equal to capital Y plus k. Now what are h and k? H and k are nothing but the points of intersection of these two lines. This is an equation of line and this is also an equation of line. So h and k are such that a1h plus b1k plus c1 equal to 0 and a2h plus b2k plus c2 equal to 0. So what we do is we solve these two equations to get the values of h and k, and hence we substitute here. Therefore dy by dx would be equal to d of capital Y by d of capital X. Therefore the equation becomes dy by dx equal to a1 into capital X plus b1 into capital Y divided by a2 into capital X plus b2 into capital Y, and thus becomes a homogeneous equation. Once again, for equation of the form dy by dx equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2 can be reduced to a homogeneous equation, the condition here is a1 by a2 should not be equal to b1 by b2. So what we do is we solve these two equations and find the points of intersection. Let us say they are h and k. We put small x equal to capital X plus h and small y equal to capital Y plus k. So dy by dx would be equal to d of capital Y by d of capital X, and hence the equation reduces to d of capital Y by d of capital X equal to a1 into capital X plus b1 times capital Y divided by a2 times capital X plus b2 times capital Y. Now this is a homogeneous form and which can be easily solved. Now if we say that a1 by a2 is equal to b1 by b2, in the previous case we considered a1 by a2 is not equal to b1 by b2. Now in this case let us say that they are equal, and let us say that they are equal to lambda. Then dy by dx equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2 would be equal to lambda times a2x plus b2y plus c1 divided by a2x plus b2y plus c2. So what we do is we substitute a2x plus b2y equal to t. Now the equation reduces to a variable separable form. So let us try to see an example. Solve the differential equation dy by dx equal to 2x plus 9y minus 20 divided by 6x plus 2y minus 10. So the differential equation is 2x plus 9y minus 20 divided by 6x plus 2y minus 10. Now we here see that the differential equation is not of the homogeneous type, but it is of the form that can be easily converted to a homogeneous form. How? Let's try to solve this. The lines 2x plus 9y minus 20 equal to 0 and 6x plus 2y minus 10 equal to 0 meet at the point 1, 2. If we solve these two equations, we get the point of intersection as 1, 2. We therefore make the following substitution. Small x equal to capital X plus 1 and y equal to capital Y plus 2. So the equation transforms to d of capital Y by d of capital X equal to 2 times capital X plus 1 plus 9 times capital Y plus 2 minus 20 divided by 6 times capital X plus 1 plus 2 times capital Y plus 2 minus 10. So this would be equal to 2x plus 9y divided by 6x plus 2y. So dy by dx, that is d of capital Y by d of capital X, is equal to 2 times capital X plus 9 times capital Y divided by 6 times capital X plus 2 times capital Y. Now this is a homogeneous equation, and when you solve it, you will get the solution as 2x minus y whole square equal to c times x plus 2y minus 5. Thus, very easily we have solved this equation. Now the next important type of differential equation is the linear differential equations. Now these are very standard differential equations, and most of the times these differential equations are asked. So this is of the form dy by dx plus p times y equal to q. Here p is the function of x and q is also a function of x. So any differential equation of this form is called as the linear differential equation. So dy by dx plus p times y equal to q, where p and q are functions of x, is called as a linear differential equation. But now what's the procedure to solve such a differential equation? What we do is we multiply both sides by e to the power of integral of p times dx. Here p is a function of x and is a coefficient of y. So what we do is we multiply both sides by e to the power of integral of p times dx. So the equation becomes e to the power of integral of p times dx into dy by dx plus py equal to q times e to the power of integral of p dx. Now this could be further written as e to the power of integral of p dx into dy by dx plus y times d by dx of e to the power of integral of p dx. Now this is because d by dx of e to the power of integral of p dx is equal to p times e to the power of integral of p dx. So this further reduces to d by dx of y into e to the power of integral of p dx. So this entire term becomes d by dx of y into e to the power of integral p dx. Now this is equal to q times e to the power of integral p dx. Now integrating both sides, we get y into e to the power of integral of p dx equal to, let us say that the integral of this is some function of x, say r. So is equal to r of x plus c. C is constant of integration. So r of x is nothing but integral of q into e to the power of integral p dx, or r dash x equal to q into e to the power of integral p dx. Now what is this e to the power of integral p dx? This is called as the integrating factor. Here p is the coefficient of y, that is, it is a function of x but is a coefficient of y. So e to the power of integral p dx is known as the integrating factor, and hence the complete solution of the differential equation is y into the integral factor is equal to the integral of q into the integral factor. Thus we can say that the complete solution is y into integrating factor equal to the integral of q into integrating factor. So we have seen how to solve a linear differential equation, but it is incomplete until we solve an example. So solve the differential equation dy by dx plus cot x into y equal to cos x. So we clearly see that this is a linear differential equation. This is of the form of dy by dx plus p times y equal to q, where p and q are functions of x. So dy by dx plus cot of x into y equal to cos x. Now we see that p is equal to cot x, q is equal to cos x. So the integrating factor is e to the power of integral p dx. So this would be equal to e to the power of integral of cot x. Now integral of cot x is nothing but ln sin x. So So this would be equal to e to the power of ln sin x. And so e to the power of ln sin x is nothing but equal to sin x. And thus integrating factor is equal to sin x. Also, q into e to the power of integral p dx would be equal to q is cos x and integrating factor is sin x. So this would be equal to cos x into sin x. Therefore, integral of q into e to the power of integral p dx would be equal to integral of cos x into sin x dx. Now to solve cos x into sin x dx, what we do is we make a substitution that sin x equal to t. So cos x dx would be equal to dt, and hence this would become integral t dt, the integral of which is 1 by 2 into t square. We write t equal to sin x here to get this as equal to 1 by 2 into sin square x. Thus the solution is y into sin x equal to 1 by 2 into sin square x plus c. Or we can write y equal to 1 by 2 into sin x plus c times cosec x. Thus this is the solution of the differential equation dy by dx plus cot x into y equal to cos x. So what we have done here is we have multiplied it with the integrating factor. The integrating factor becomes sin x, and through that we have solved this differential equation.